I am Nusheen Puya with the Washington Department of Ecology, and I will be moderating for stormwater compliance and monitoring on a floating bridge with Gordon MacDonald and Paul Fendt, both with Parametrix. Please type your questions in the Q&A box, and as time permits, the presenters will answer your questions after the presentation. Take it away, Gordon and Paul.
I'm Gordon MacDonald, and I'm joined with Paul. Paul is our stormwater and water resources manager, and as he is it for Parametrix, not it, but he manages and leads that for Parametrix. I'm a transportation engineer, and both of us have worked on Washington State Department of Transportation's SR 520 floating bridge replacement and HOV program. And I was involved in the preliminary design of the floating bridge and freeway segments, and then later the design build elements of some of the projects. And Paul was involved in the early stormwater design and the AKART study. And then post construction of the floating bridge, he was involved in the stormwater monitoring. And we'll get into it right now. There is a SR 520 is a major east-west corridor across Lake Washington. And because of the depth of the lake and the depth of the sediments at the bottom of the lake, Washington Department of Transportation opted to build a floating bridge in this corridor. And a floating bridge is actually floating on top of 33 longitudinal pontoons that extend parallel to the roadway corridor. And you'll see on the left side of the floating bridge, those little bump out things are supplemental stability pontoons. I look at those like water wings. They prevent the floating bridge from rocking from side to side. Here is a shot of the underside of the roadway deck. The deck is above, and it's supported on structural columns that rest on these floating pontoons. On the left are the longitudinal pontoons, and on the right, looking down the right side of the picture, is a row of supplemental stability pontoons. By way of note, the roadway section resting on the floating bridge is the longest floating bridge in the world, over 7,700 feet. And it's high on the east and west side of the bridge where it connects to land or the approach structures, and it's flat near the lake at the bottom. And so that raises some concerns and some unique challenges, because you can't convey and treat stormwater the way you would in a landside environment. So how does stormwater get from the deck of the floating bridge down to the lake level? We installed modified catch basins. So what I mean by modified catch basin, it has a very deep or deeper than normal sump from the invert down. The purpose of that is to collect more grit and sediment from the roadside and allows it to settle out before going down the conveyance pipes. Well, the conveyance pipe is connected to the bottom of the roadway deck, and then down the structural columns to the supplemental stability pontoons, and then across that and into the center part of the supplemental stability pontoons to what we call a stormwater lagoon. And we'll talk more about why that's important in the overall treatment train a little bit later. As part of the post-construction requirement, is WSDOT and the Department of Ecology required that we monitor stormwater conveyance and treatment on the bridge for an extended period of time. There were 3 monitoring sites, one on the west shown in yellow. That's the contributing area that would flow to that monitoring site. One at the middle of the bridge shown in blue, and the contributing drainage area shown in red is on the east side of the bridge. Now, looking at the floating bridge in profile, one of the requirements of our AKART study was that we have these 2 of the monitoring stations on sloped portions of the roadway. So we located one on the west high rise and one on the east high rise, this is clear to see that the ends of the bridge are much higher than the middle part. And so there was one on the flat portion of the bridge. These monitoring sites were equipped with several different things. First of all, we diverted the water that was normally in the conveyance system to what it was called a weir box, and then from the weir box out into the stormwater lagoon. This weir box slowed the stormwater down enough so that we could make water samples, take water samples, and then we were able to collect the samples, and then through telemetry, we were able to convey the stormwater data to Parametrix and our subs, helping us out with the stormwater monitoring. So as I talked about before, there were some unique issues with conveying and treating stormwater. So we had to develop what is known as AKART, all known, available, and reasonable methods of prevention, control, and treatment, or AKART. So early on, we looked at different alternatives for combinations of treatment alternatives. And one was media filtration with conventional sweeping. Another one was catch basin filtration, also with conventional sweeping. And these modified catch basins with conventional sweeping, and also high efficiency sweeping and modified catch basin cleaning. And we'll talk about what that high efficiency sweeping really means a little bit later. But in the end, our proposed Acart treatment train included high efficiency sweeping, modified catch basins, that's with the larger than normal sump in the catch basin, and spill containment lagoons. Now, these spill containment lagoons are really what Paul is going to talk to us about. That's the hole in the middle of those supplemental stability pontoons. Go ahead, Paul.
Okay, thanks, Gordon. So when we, as part of the AKART analysis, once you have AKART and you're able to use mixing zones. And so as part of the agreement and the approval for the bridge, we had defined a mixing zone that was based on discharging into the lagoons and then mixing with lake water underneath the lagoons. And so we ended up with a concentration at the mixing zone boundary that was allowable. And that concentration was based on started being based on what typical roadway runoff would look like, with sort of treatments to it. So next slide. So basically what happened is that we back calculated from the edge of the mixing zone what the concentrations were that would be allowable at the edge of the mixing zone, and back calculated what the resultant concentrations would need to be for the water quality design storm with a certain concentration. And so the purpose of this was for Ecology to confirm that what our performance of our system was going to be able to reasonably meet the mixing zone concentration at the edge of the mixing zone. In order to do that, we were different targets were established that are shown in this table, and these targets were based on if the concentrations that we monitored were these numbers or lower, then we would be expecting to meet our mixing zone. And then remembering that these are based on the water quality design storm. So this concentration in the water quality design storm mixed in the lake and in the mixing zone result in complying with our mixing zone responsibilities, or our edge of mixing zone responsibilities. So I highlighted the copper. We're focused a lot of what we're going to talk about the rest of the way on copper. So what we needed to do and what the agreement was is that we had to, during the course of our monitoring, where we're going to monitor 22 storms, we could not exceed this number, 67.7 parts per billion, more than once. And then mid-span is a slightly different size basin and so on, a different mixing zone. So it was a slightly higher number. So we're really focused on the 67.7. Next. So what does high efficiency sweeping mean? So the sweeping that was identified in the AKART analysis is to do it once a month, and by schedule, WSDOT does it once during the first 4 days of the month. They wouldn't tell us exactly which one. They sweep the entire road surface, seat to seat, which means in front of those, basically the ecology block walls to wall, inside and outside the shoulders, a little bit over 8,000 feet. So they go up the approaches. There's a vehicle train with 5 vehicles that goes at 6 to 9 miles an hour. So they do it in the middle of the night. And of course, there's a number of different vehicles like the warning vehicles, one vehicle that picks up the bigger stuff, and then the real heart of this, the regenerative air vacuum sweeper that does all the sweeper, and then basically the rear guard for this approach. So it's a 5 vehicle train, goes up and down the bridge once a month in the middle of the night. Next slide. So our AKART monitoring objective was meet that dilution target that I mentioned, and we could only have one event that was allowed to exceed. And what we were doing in the monitoring program was evaluating sweeping and oversized catch basins, how well they were doing. By the statistics that were identified, we needed to do 22 events over the course of that. And so it's 22 events total at the 3 stations that qualified. And then we had to set everything up on the bridge. So you saw the setups that we had for the weir boxes that were measuring the flows, and then identifying, and cutting into the drainage pipes that were coming off of the road surface, and then intercepting that water and sampling that stormwater and sending it in. We needed to calibrate the systems. It was pretty easy because it was all impervious surface, but we did find a little bit of difference based on some delays with storage of water actually on the surface of the pavement and so on. So we made those adjustments and then set up all the other logistics about getting ready to sample. And then we cleaned out the catch basins right before we started. So we were starting with basically kind of a clean slate. Next. So this is a result of the calibration. So you can see that the heavy bar is what the theoretical runoff would be. And we had slightly different numbers than that. But the purpose of this was to make sure that we were calibrating what our expected runoff would be against the rain gauges that were about a mile away. And so that we were collecting, that we could program the samplers and so on to get the right sampling regime so that we would have the right sample size for our mixed samples. Next slide. So now we're going to talk about some results. So these are the basic results of dissolved copper in the stations by season. And season it was pretty much by the calendar season, so it was December to February and so on. And so the first season is the winter season, second, third is the summer season, and the fourth, of course, is the fall. And the slide on the right, or the chart on the right, is just showing the same thing as the left, only zoomed in, so you can see a little more detail on where our concentrations were. So you can see they were pretty consistently and basically in the teens, other than a couple of outliers in the summertime. Next slide. And here's the same thing for zinc. Again, our concentrations versus our seasons. And I'll just pause for a moment so you can look at them. And you can see as you zoom in that our numbers were fairly low in the double digits, but kind of in the low 20s, 30s, 40s, and so on, other than a couple of events in the summertime that we'll get into here in a little bit. Next slide. So in our analysis, we only had one event that exceeded of the 66. So it'd be 3 stations times the 22 events. We only had one station and one event where we exceeded the copper target. All the other constituents that you saw on that original chart were met for all the sampling events. And so as we described it, our program is confirmed that our predicted analyses of what we would have as far as concentrations at the edge of the mixing zone were confirmed by the concentrations that we were getting. And they're actually quite, other than the one event, they were generally quite a bit lower than what was expected. So let's dig into the data a little bit here. Next slide. So the first thing we looked at is to see whether or not if there was a difference in the concentrations, if there were a certain number of days since we swept. And as I mentioned, they could have swept the first, second, third, or fourth day of the month, and you would think that it really wouldn't matter that much. And so then we would say, well, we didn't know when they did it, so we had to assume that every event was one of those 4 days. And so we looked at the number of days since sweeping, We were comparing the days sweeping against what we called the total mass per acre, and that we did it by mass of the concentration of the constituent that we're evaluating to normalize the different sizes. So because the basins were slightly different sizes, that we looked kind of more toward the loading rather than the concentrations in this analysis. In any event, you can see that the trends, depending on which day of the week we guessed that they, or which day of the month of the first 4 that we guessed that they were going to monitor, that the trends went up and down depending on on how long it had been from the start since the last sweeping. So that just tells me that it's really not strongly dependent on how many days since sweeping. That sweeping is good, and there's not really a strong correlation between earlier in the month and later in the month. Next slide. So then the next thing we looked at is that how many days since the clean out of those oversized catch basins, whether or not there were any trends that developed as far as, again, this is dissolved copper, and it's by minimum days since the oversized catch basins were cleaned out. And you can see that the data over the life of the first year, and then we did it again a second year. So we monitored over 2 years. And so as we monitored over the 2 years, we were looking at, the first year and the second year at the different stations, and you can see where the trend lines end up, and that there really wasn't a difference that was observed at all over the course of the year relative to how long it had been since the catch basin had cleaned out. So let's go to the next slide. So then we also looked at this over the whole 2 years of the monitoring period and so on to see whether or not there were any changes. So rather than just saying since we cleaned out the catch basins, this is the life of the project. So over the two-year life of the sweeping and the catch basin cleaning and so on. And generally you can see that this has copper and zinc on it, copper in blue and zinc in green. And you see there's just basically a slight downward trend in the concentrations during the life of the project. So you can decide how to interpret that in any way you like, but over the life of the project, there was a slight downward trend in the lowering of the concentration, or lowering of the, what I'd say, of the total mass per acre. Next slide. So then the next part is we're looking at how many antecedent days of no rain there was before each one of the events. And we didn't have any event that had less than or fewer than 7 days of antecedent, or more than 7 days of antecedents before them. And again, this is just copper. And so we're looking at somewhere between either 0 and 7 days of antecedents over the life of each, over the course of the 22 events over 2 years, and then how many days it had been since it had rained before. And in this case, you can see there was a slight upward trend in general on the first couple of the stations as you got further away from the last antecedent rainfall. And then no trend. The blue, the green, the dots, the blue dots on the bottom are the station that was sitting in the bottom in the flat part of the bridge. Next slide. So this is one of the more interesting things that we saw and found, and that was that we actually looked at real automobile traffic counts before we before the sampling event. And so we looked at a 24-hour count before we started sampling the storm, and then the next slide we did something else, but we're not ready to go to the next slide yet. But anyway, and so we see that basically this was kind of looking at if there's more cars on the road, would we get higher concentrations? And this was very immediate. It was the 24 hours before we monitored. So you can see the trend lines on here. Again, this is dissolved copper, and there's basically no trend or a slightly lowering trend as you get to more cars in the 24-hour time frame, not before the sampling started. But let's go to the next slide. We see the opposite or slight upward trend in the concentrations of the traffic counts during the storm event that we were monitoring. So when we were monitoring, the number of cars that were on the road during the period when we were monitoring stormwater, as that increased, the concentrations trended upward slightly. Next slide. So this is this is when we started digging into, you know, we did mention that we had one event that exceeded the 67.7. It was in the around 72 or 73, so slight exceedance and so on. So we're starting to look at and say, well, what was up with that? What happened there? And because that could give us some, you know, a little bit of insight into what are the things that might matter on the road as far as antecedents or rainfall amounts and so on and so forth. So you can see here, these are all the events, and these are the runoff volumes that came from each of those events on this chart. And you can see that those two high events were way over on the left side, which means they were high concentrations with low amounts of stormwater. And that's not unexpected. That's something that we do see or believe, is that if you have a certain amount of loading and you have a rainfall that can wash it off and a very small amount of water, you might end up with a high concentration. And that bears itself out here in that these were some of the lower stormwater runoff amounts during the course of the study. And then these events were also occurred in the summertime.
Interesting to note that green dot is on the east high rise.
Yeah.
Larger contributing area.
And then the red dot, of course, is on the other high rise, and that you see all the blue dots that were in the middle, all kind of, they have the smaller rainfall amount, but you know that they're it's about the same size basin, but there's just different results that we have based on which one of those basins. So there is a difference between the middle of the bridge and the two approaches. Next slide. So this is the other thing we found that was actually fairly interesting. And so you remember the slide we had on number of antecedent days, and we didn't have any event that was more than 7 days away. But we also looked at what was the total rainfall amount that occurred in the 30 days before the event. And so this is the summary of every event. We added up how much it rained in that time period before the day we sampled it. And what you can see, of course, is that on the far left is our offending event, and that one is the one that occurred that had the smallest amount of rain in the 30 days before the storm. So you can kind of put that somewhere in between. It was in the summertime, and that it was actually a very dry period, even though it had rained and 7 days or less before that event. It still was a very small amount of rain. There was very little rain that occurred for a long time. So there just wasn't any water around to wash this off. Next slide. So our summary in this is that we did achieve the goal that we had agreed to with Ecology. AKART objectives were achieved. A couple of things about it working and so on. It's really somewhat inconclusive if more or less sweeping is warranted. If you remember the trends going up and down depending on which day of the month we guessed that they had swept and so on. So there wasn't really a strong ability to say that 25 days was good and 20 was bad or anything or the reverse. We did the amount of sediment that we found in the deep catch basins supported annual cleaning. They were getting pretty close to being full when we cleaned them out. So there is sediment out there. And so we had about the right size, and we found that, having larger catch basins mattered and helped us. There's one thing, I'm going to skip over the yellow thing for a second and say that, it's useful to explore the difference between stations. There's not really a strong belief. It's the same number of cars, the same width of pavement, everything's the same, other than it's steep rather than flat. And so there is a difference. Generally, the flat station in the middle of the bridge had slightly lower concentrations than the ones on the approaches and so on. So it's definitely interesting and worth exploring a little bit different and trying to compare those things. So then the last thing I want to focus on is as I talked about setting a different target includes variable runoff. So if you remember at the beginning, we were talking about how that the mixing zone was based on a water quality design event. So it's the total volume for the water quality design storm with the target concentration into the mixing zone. So if you have a mixing zone, it's the variables on it are the volume of water and the concentrations are, and then the hydrodynamics that are going on to get to the mixing zone and where that mixing zone edge would be. And so if you have a smaller amount of water with the same concentration, you actually have a lower concentration at the mixing zone. And so all those numbers, that 67.7 was based on the idea that we would be at the edge of the mixing zone with a full water quality design storm. When in fact that fending event that was the highest concentration that exceeded was 1/10 the volume of the water quality design storm. So if you actually do the math, it's roughly means that we were 1/10 of the, even with that concentration that was just around the target, we were about 1/10 of the actual allowable concentration at the edge of the mixing zone. So we were clobbering the requirements at the edges of the mixing zone with our results. So we did really well. And that would be, if we would have exceeded twice, we would have had to gone into adaptive management. And with adaptive management, part of what we would have described and discussed is actually looking at the variable volumes of runoff that are relating to these, to each of these concentrations, rather than just a set thing that says the only volume we could consider would be the water quality design storm and that concentration. So that's that's a summary of the work that we did there, and we can answer some questions if you have any.
Thank you, Paul and Gordon, for that. That was great. We do have time for maybe 1 or 2 questions, and I will go ahead and read through these. I'm sorry, I'm not going to get to everybody's question. One of the questions we had here, sorry, scrolling down. Did you, when you set up the treatment train to test, did you set up the whole system, or was it just on one section of the bridge to confirm success?
We set up the whole system. We needed to build the bridge to test it. And so we had to build everything.
Got it. Let's see. Are you expecting that you'll be asked by Ecology or WSDOT to modify the mixing zone compliance approach in response to the recent research findings on the effect of higher anti-ozonation chemicals on salmon mortality?
We've met the AKART responsibility, and Ecology has accepted the AKART, and so there's, at this moment, I haven't heard of any expectation around adjusting or changing the mixing zone. No.
Thank you. Another question would be, will the targeted water quality numbers be adjusted after the light rail is installed?
Unlikely.
Okay.
We accounted for light rail in that design, and so it's unlikely. You're right.
Thank you. Were there any lagoons that received unswept bridge runoff for comparison?
I missed a word in there. You said, were there any lagoons that
received unswept bridge runoff
unswept?
Comparison?
No.
No? Okay. Yeah, I think that's pretty much all the questions that we got in the chat. I want to thank you guys for your presentation. It was very informative. If you have any additional questions, please contact the presenters. Their contact information can be found in the program and on the Feed Loop app. Thanks again, and I hope you enjoy the rest of Municon.